Welcome back. The objective of this video is to explore the application of a tangent line problem. Here in sample 9, they ask us to describe the graph and the rate of change for each of the following graphs shown below. So in graph A, here they ask the graph of h is what? Well, we can see here that in the graph of h, our y values at the moment are all positive. So I would say we've got positive y values. Visually, we can see that this is concave up, and we can see that the graph is decreasing. So our y values, as we read from left to right, are falling as our x's are increasing. Now the rate of change here, the rate of change is talking about slope. So think about tangent lines or secant lines. So the rate of change, the slope is negative, and the rate of change though is increasing because our tangent lines are becoming less and less negative. So as our tangent lines become less negative, we can say the rate of change is actually increasing. In sample B, the graph of k, we see that the graph here, the y values are all negative. So I would say we've got negative y values. I would say that it is increasing because as we read from our x's increase, our y's also increase. So it is increasing. And it is concave down. As for the rate of change, again, slope, so what's happening to our tangent lines here? We've got really steep tangent lines, and then they become less steep and flatter still. So I would say that the rate of change, while it's positive, those all have positive slopes, I would say it's decreasing. Let's take a look at a sample problem. In example 10, the traffic flow at a particular intersection is modeled by the function defined by f of t equals 96 plus 5 sine of t over 2 for 0 to 30 minutes. We're going to use our calculator here to calculate some things. So when you do that, make sure you go to mode and put your calculator in radian mode. There's a good chance your calculator is in degree mode. So question A, what is the average rate of change of the traffic flow over the time from 3 to 8 seconds? Indicate the units of measure. What does this rate tell you about the flow of traffic? So we're going to have to put 3 into our function. We're going to have to put 8 into our function and calculate the slope. So we need to find the slope to find our average rate of change. So we'll do f of 8 minus f of 3 all over 8 minus 3. Well, f of 8, we're going to have to put 8 into our calculator. So 96 plus 5 sine of 8 over 2, which is 4. And I get 92.216. And f of 3, so 5 sine of 3 halves, 96 plus 5 sine of 3 halves. I put that in my calculator. I get 100.987 all over 5. I do that arithmetic, and I get an average rate of change of negative, well, 1.75. This is really negative 8.771 all divided by 5, so negative 1.754 is our average rate of change. So we have a negative rate of change, so traffic flow is decreasing. By 1.754 vehicles per minute from 3 to 8 seconds. Is it possible to find the rate of change at a specific time? Why or why not? Well, in order to find a specific time, that would be the instantaneous rate of change. And we don't have the tools to do that right now. We could find an estimate by choosing times that are super close together, like 3 seconds and 3.1 seconds, and calculating the average rate of change, and that would give us an estimate. Okay, so that would be one of the possibilities. Let's explore the rates of change at 2 points over small intervals. Well, that's what we just said. If we chose really small intervals to find the average rate of change, we'd get an estimate of the instantaneous rate of change. So that's what we're going to do here. So we're going to try and find out what it is at t equals 8 by looking at really small intervals, or things that are super close to 8 seconds, and evaluating those. So we're going to first look at 8 to 8.1 seconds. Then we'll look at 8 to 8.01 and 8 to 8.001. So we're getting closer and closer to 8 seconds. We'll evaluate the trend, and we'll make a hypothesis as to what the instantaneous rate of change is at 8 seconds. So we find the y values for 8.1 seconds, and f of 8 we already have from the previous problem, and we find our average rate of change. So putting 8.1 in, I get 92.057 minus f of 8, which is 92.216. I miswrote that. All over 0.1, and we get approximately a negative 1.586. So next we'll do the exact same thing, but for 8 and 8.01 seconds. So we find the y value for 8.01. F of 8.01 is 92.1997 minus f of 8, or 92.216, all over our change in x, which is just 0.01. Put that in our calculator, and we get negative 1.631. And then we're going to repeat the process again for the times between 8 and 8.001. So our secant line, the 2 points we're choosing, are getting super close to just being right on top of 8. So we're trying to find an estimate of the instantaneous rate of change. So we find the y value for 8.001, our change in y. So we get 92.214 minus the 92.216 all over our change in x, which is 0.001. So those are super close to each other. So that secant line is almost a tangent line, and we get negative 1.646. So we're heading, it looks like we're heading pretty close to negative 1.65. Seem to be heading in that direction. So our summary, our findings seem to indicate that at 8 minutes we estimate the traffic flow to be approximately a negative 1.646 vehicles per minute. I know it's restating the obvious, but traffic flow is decreasing at that rate. And that concludes our sample on the application of the tangent line. And we'll get some more practice with this when I see you in class.